Today's class is thin gauge pressure vessels and beam design. But let's start the first topic, which is thin gauge pressure vessel. What's it that about? Basically, a tank loaded with pressurized fluid. Pressurized fluid. Fluid can be water, can be gasoline, or can be air, gas. All of that we call fluid. And the material make up the tank is subjected to loading from all directions. Material subjected to loading from all direction. So to give you an idea what is that about, I took a picture on the Alico Road between the US 41 and I-75 on Alico Road. And as you can see here, that propane tank along the Alico Road, they have two tanks. If you see what is that about, that is one time of the single pressure vessels, and in this case the fluid is propane in there. So that one of the application for the first topic of today's class. So the question is how we ensure that tank is safe. Otherwise, you can see very dangerous if the safety is compromised. In this situation, it can cause explosion, etc. So with that here, we go back to the lecture and give some more example of what are the vessel that we consider that is single pressure vessel. So you get what some example. Air tank. Or it can be for the kids' birthday, it balloon, or we even us for the birthdays we also go with balloon, or we play with the basketball, etc. So basketball. Or you drink soda in the can, so it's also the soda can. As you can see, the metal make up the soda is very thin, and under the pressure fluids is the soft drink. Soda can, or even the hot dog to eat. So as you can see that hot dog, there is a thin layer outside that have a pressure, and that we can consider that is a single pressure vessel. It may not carry the fluid, but that is a single pressure vessel. But our topic is focused on the tank loaded with the pressurized fluid. And the first application, that is the example that I show you, the issue with the cylindrical single pressure vessel. So let's call this one, let's rename that is thin TW PV single pressure vessel. So from that we can write down here the first application, and we want to investigate that is cylindrical thin gauge pressure vessels, as the one I showed you in Alico Road here. So let's cut the cylindrical with 3D sketch. So we have here, and even it's thin, I assume that, I draw the goal of the cylindrical here big enough so that we can easy to see that here. And the thickness of the cylindrical here, we call that T, as you can see. And then the radius from the center to the goal, that we can call it R. So nothing new to us in there, right? So radius R. So what do we have in here? How we define that is a single? Why it think when it consider a single? So for single pressure vessel, we need to have the inner radius of the cylindrical. So inner, just like I show here, inner here, just go to the inner side of the wall of the tank over the T, the thickness of the tank. It have to be very large. This ratio have very large. To consider thin is at least 10. So the radius very large compared to the thickness of the gold that we can call thin gold. So as you can see, as from that equation, as you can see, as T going down, then the denominator going down, then the I become very big. So we can say that here the radius of inner approximately equal to the radius of the outer. Because T very small. For example, if we have the the inner radius is 1 meter, which is 1000 millimeter, and then the thickness is 2 millimeter. Then as you can see, now the outer radius is equal to inner radius plus T, the thickness. So it equal to 1000 plus 2 millimeter, so 1002 millimeter. So as you can see, very approximate between the radius of inner and outer for the cylindrical tank. So from that one, we can have the stress on that member, here. And what happened to the stress of the member? So let's consider a point on that member, Then we have the state of block. So by definition in your book, the one along the hoop, not longitudinal axis, along the hoop, then they call that the sigma 1. And for us, it's also same. I'm going to down here sigma h that I'm going to talk in the next few minutes. And then the normal stress along the longitudinal axis of the cylindrical that we call sigma 2. And as you can see that both are principal stresses. And for us here, we call that a sigma longitudinal. So in the book, they call sigma 1, sigma 2. And in this case, normally we do, as you can see here, we call it sigma, the hoop stress and longitudinal stress. And so sigma 1 is actually sigma of the hoop, along the hoop. And then sigma 2 is the longitudinal normal stress. So keep that in mind between the book and what we are calling here. So let's investigate the hoop stress first. The hoop stress. What does that mean? We have it sigma 1 equals sigma h, and I just brought it in state of stress block on the cylindrical just previously here on the cylindrical tank. So for the hoop stress, let me cut this tank along the longitudinals, and what we see it in here, if we cut that members, then we can draw the half of that member. It could be like this. And again, I exaggerate the thickness of the member. Half of that. And when we cut that, as you can see, what do we have in terms of the free body diagram? When we cut that member, it's exposed to the hoop stress, which is sigma 1 or sigma h, and we just write down on the material. On the tank. And that is sigma h, and you can see there of the hoop. And then why we had that? Because that is the pressurized fluid. So the pressure we represent on that, the inner pressure that apply from the fluid on the wall, that is P. Then we have the pressure P apply to the wall of the tank, and that one we call that is P. And let's define that here. P is stand for inner pressure. Inner pressure. So from that we can have the, if we call the length of this cylindrical single pressure vessel is L and the thickness is T, then we have the area of the material of the cut. The area on the material of the cut. And you can see one side, it will be the T, the thickness, the area, the blue area on this side. Here you can see that equal to L, the length, times T, because that is rectangle, and both sides we have also the side in here, so that it will be 2LT, and that we call that is the area 1. We call it area 1, 2LT. And we also have the areas for the fluid at that cut. Excuse me. At that cut. So you can see in this area in the middle, for the fluid, it's a rectangle. The width is 2 radius, the diameter of the inner circle, and then the length of this rectangle also L. So from that we can have the area in the middle here, and that we call it area 2 equal to diameter times the length. Diameter, as you can see, that is 2 radius times the length of the cylindrical tank. So that's what we have for the free body diagram and the areas. Now with that free body diagram we can apply the equilibrium for this one. Equation for that free body diagram. In this case, let's sum up on the force in y direction. Assume going up equal to 0, and that is assume going up positive, and by equilibrium sum of all the forces in y direction equal to 0. And that we know let's put down here, elaborate that equation. So 0 equal to the red part, sigma hoop, times the areas equal to the force, if you recall that. So sigma H times the area, in this case A1, the total for both sides of the single. So sigma hoop times the area A1, it will be equal to the P, the pressure, the inner pressure due to the fluid going down. So it will be negative P, pressure P, time the area that applied to, that is A2. You may not convince why A2, because the goal, it applies throughout the goal, it not excuse me, not the horizontal area when we cut through. Let me show that why is that here. So if we have a triangle here, and that is the curve after we cut, right? And then we have the pressure, it's always perpendicular to the goal. Pressure is always perpendicular to the face here. And of course, if we sum up all that one in the y direction, as you can see, not all is the go to the y direction, so you have to cosine of some of them. So with that, actually, when you project that in y direction, it become horizontal, and the load of P can be equivalent to this. If we sum all of that from here to there, we sum all of the force in y direction, the pressure actually apply on the goal, which is not always in y direction. If we project that single, it becomes the horizontal area, that is A2 that we are talking about. So from that, we can plug in the A1 and A2 so that we can have the equation. So what we have here, as you can see, equals 0. So I print one side out. So we have sigma hoop A1 equal to P A2. So sigma hoop 2LT, that is the areas for A1, equal to P, and that is 2 I L. And we simplify the L and 2, so we have the hoop stress along the hoop of the cylindrical, it equal to P times the inner radius divided by the thickness of the goal. So that is the first equation. So with the inner pressure, we can be able to determine, and the geometry, which is the inner radius of the goal and the thickness of the goal, we are be able to determine what is the stress along the hoop of that cylindrical tank. So that's the first important equation we have.